Very good morning, students. Today we will discuss the analysis of algorithm. There are two kinds of analysis that we have to do. One is in iterative algorithm and another is recursive algorithm. So, in my last discussion, I have discussed the iterative one. Today, we will discuss the recursive, how the recursive algorithm evaluated and how we go for the time complexity and to find out the time complexity as well. This is very simple. If we go through the internals of any algorithm, of a recursive kind of algorithm, we will find that how it works, how the time complexity has to be calculated. Though it is not depend on the programming part, it is completely depend on the mathematical part of that calculation. So we will move on one by one. Suppose I have a very small program, just to understand the concept. I want to find out a factorial of any number using the recursive algorithm. How it works actually. That means what we call a function within a function that calls itself. So the mother function having a child function, again that child function calls the mother function. I will explain you one by one. Suppose I have passed here 5. I have passed here 5. So if 5 is not equal to 1, then the factorial is, if it is equal to 1, then it will return 1. Okay. Else factorial is equal to n into factorial n minus 1. Now what happens here? It will be 5, and in the memory this factorial now will be a mother function and it will call this factorial with a value 4. That means what happens? So when it will call 4, then it is not 4. Again here it will be 4. It will be factorial 4 minus 1. Again in the memory it will be 3. So how it works? It is the first block when I call it with a 5. So here it is 5 into factorial 4. So by 4 again in this whole block will inflated in the memory like this, and here it will be 4 into again factorial 3. So that's the beauty, and it will moves on. I will explain in a proper format that very beginners, those who don't know anything about the factorial or any recursive calculation, I will keep in mind that my students, they know nothing about the recursive kind of algorithm. So I will explain in such a manner that everybody can understand. And this is very interesting as well. Now we move on to the another part. This is the code. Now the beauty is that suppose if I take it as a, just a minute, I will take some another color. The color. Okay. Now if I put here, suppose 5. Then what have happened? Here it is not matched. So here it is 5. And here the factorial, what happened? 4. So here it will be 4. So this part, this whole block again inflated here, and here it will be 4. So if it is 4, then factorial is not equal to 1, n is not equal to 1, so it will not able to return 1. Now factorial is equal to, now it will be 4 and here it is 3. Okay, this is very simple. Again when it calls, this is a calling function, so it will inflate the same code in the memory, and now this will be 3 because of this function 3. So n is not equal to, though n is equal to 3, so n is not equal to 1. So factorial, here it will be 3, here it will be 3, and this will be factorial 3 minus 1, so that this will be 2. So though again it is a mother function and calling function, it calls here, it will be 2. The function factorial 2, that means n is not equal to 1, so that it will be 2 and this is factorial 2 minus 1, so that this will be 1. Now interesting part is that if this is n minus 1, so this is calling function and this will call this function with a value 1. Now actually we in any recursive, it is a back propagating approach, from the bottom to top approach. The output comes from the bottom to top approach. So that this is 1. Now n is equal to 1. Beautiful part is that. So if n is equal to 1, the factorial 1, now this function, who is the mother function of this function? Certainly this function, this is the mother function or the calling function. So it will return to whom? To its calling function. So 1 will be finally factorial is equal to 1, factorial is equal to 1. This part won't execute because of n is equal to 1. So factorial n is equal to 1 and it will return to any function. When it returns to its mother function, that means the calling function. So it will return 1 and by this will be 1. Now what we call, when it returns, this function completely burns out. Completely burns out. No existence in the RAM. And it will return. Now here it is 1. So now what happens? 2 into 1. So the total value is equal to 2. Now this factorial is equal to 2. So this function will return, now this function completes end of the factorial. That means it's complete because it was open, because this function has inflated this one. So here it is unfinished, so it was open. Now when it is burns out, this will come to here as a 1. So 2 into 1, 2. Now it will return to its mother function. This one, this fourth one, inflated fourth one. Now it will return to whom it will return? This will return to its mother function. So here it is 2 into 1, 2. That means it will return 2 here. Completely here it will return 2. So if it is 2, then n into 3, 3 into 2, that means 6. So 6 value, similar way, the end of the factorial. So this was burns out. Now the term comes here. This will also burns out. It will return the value 6 to its mother function and this will completely burns out in the RAM. So now here it will be 6 to move on to here. So here it will be 6 in whole calling function. Though it is burns out, so this will be 6. So 4 into 6, 24. 24, this is the inflated function. This opens because of this. Then now this is burns out. So this is 4 into 6, that means 24. So this will return 24 to its mother function, 24 to its mother function, and here we will get 24 and 24 into 5, 120. This whole factorial will be 120 and it will return to main 120, and by this we got the, and it will return to main and we can take out the printout 120. So don't you think this is a completely back propagating approach or bottom to top approach? Because until and unless this function burns out, this will not complete. Until and unless this burns out, this will not complete. And until and unless this not complete, this will not complete. Not burns out, this is not complete. So this way, this back approach, bottom to top approach, this gives us an answer of the recursive approach. Now the interesting part is that we have to calculate the time complexity of this kind of all the algorithm. There are plenty of algorithms, those who are best fitted using the recursive nature. If we do the recursive nature, we will have a much more lesser amount of coding to have this kind of approach. This is the beauty of this kind of approach, recursive algorithm. Now we move on to the recursive algorithm. How we calculate the total time, from total time how we calculate the time complexity, and all. We move on to this. Is all clear to all of you, I think. So this is very simple. It is a bottom to up approach, and by that we calculate the total time complexity. Here it is not actually a time complexity we are calculating. We will calculate the first, we will calculate the total time, then we will move on to the time complexity. Now move on to this one. Now suppose I have, this is now you can easily think about that, this is a recursive approach, because this is a one function and same function is over here. So now if I send 5, so it is greater than 0, print 5, then 4, again it will be called by 4, the 4. So this is a recursive, okay. So this is a completely recursive in nature. So this is a time. Now we will calculate the total time. How we calculate? So this is actually what we call, we call total time Tn. Total time Tn. Because this will give you the time, total time Tn. Now to evaluate, everyone needs at least one certain clock pulse. So this is 1, because it checks n is greater than 0, so 1 stroke. This is again 1, and here it is total time, we call it as a total time. So this is total time minus 1, because if it is 5, then it is 4, next time it will be 3, next time it will be 2, next time it will be 1, next time it will be 0, and so on, so on, so on. So we can easily call it as a Tn. Now what we have to do, for one particular snap, we have to find out the summation of all. So what we have got, Tn is equal to, this is total time because this is the function name. So Tn is equal to 2, numeric value 2 plus Tn minus 1. So what we can say, 2 Tn minus 1 plus 2. So though it is a constant value 2, in place of that we can write 1. Why? It is not put much more value, add-on value into this whole part. If you say 100, so this is not the important part. If we say 10 to the power square, that is a different issue. But if we say 10, this just add on to the value. So any numeric value we can call it as a 1. So this is how we find out the total time from any recursive kind of algorithm, and that is the beauty of this kind. We have to go for the summation of all. So I will give you another example, and we will calculate all the time complexity. Basically, by 3 ways we calculate the time complexity. The first one we call it as a decision tree. The second one we call it back substitution method or back propagation method. Back substitution method, by that we can calculate the time complexity. And third one is most important, we call it as a Master's theorem. But Master's theorem only can calculate in certain formulas. It cannot calculate all kind of approaches. So we will start with the decision tree, back substitution method. First we will find out the total time, then from that we will calculate the time complexity. So now we move on to the another part. This is a beautiful part that we have to say that what we call decision tree method, you can note down. The second one called back substitution method or back propagation method, and third one is the Master's theorem. So if time permits, I will explain Master's theorem, or in the my next video I will share the Master's theorem in detail. So the first one we call it as a decision tree. How we move on to the decision tree? Suppose I take an example, right? This is a beautiful example, and we can work on to that. I have quoted one function, that is recurrence n. That means if I say it is 100, recurrence n 100, that means we move on, right? Now if n is greater than 0, we introduce one for loop within this. So for I is equal to 0, I is less than n, I plus plus. printf n. Now what happens? If I pass on n, that means it will start from 0 to 99. The total number of loops will be 100 and I plus plus. And this will print 100 times starting from 0 to 99. Next time it will call recurrence n minus 1. That means 100 minus 1. So it will call 99 and again it will move 0 to 99 and it will again repeat 0 to 98. That means again 99 loops and so on. I think all of you understand what I mean. 100, 0 to 99, 0 to 99 times it will print. I call this recurrence code by n minus 1. So 100 minus 1, it will call 99. The next time greater than 0, 99 is greater than 0. So it will move 0 to less than 99. That means 98 times. So 0 to 98, that means including 0, it will be again 99 times. So it will print 0 to 98. Next time it will print 0 to 97. Next time it will print 0 to 96, 0 to 95, 94 and so on, so on, so on. Now how we calculate the total time from here? So again, this is a Tn, all you can understand. Each and every time it produces only one clock pulse, one slot. Now 0 to less than n, that means you can say, here you can write n or n plus 1. If you write n plus 1, that means what? This is very beautiful. I need to discuss why it is n plus 1, because all of you can say that, sir, it is 0 to 99, that means we should write n. No. What happens actually, when it is 99, so it is less than 99, it prints. Now it moves on to here, it will 100 and it is less than, I is less than n, that means it won't satisfy, it comes out here. That means again one stroke, that means total 101 stroke, 100 stroke, that is a right case. That means 0, yes, 1, yes, 2, yes, 3, yes. Similarly, 96, yes, 97, yes, 98, yes, 99, yes. That means 0 to 99, yes. Now again it will increment 100. So 100, no, moves out. So that means this statement actually moves 101 times. 0 to 99, 100, but moves out, though it is 0 to n plus 1. So that we write it is n plus 1, and similarly we write this is n, because this will print 0 to 99 and this will move 0 to 100. I think all of you clear it. Now again it is recurrence n minus 1. Similarly I call it as a recursive. So here it is Tn minus 1. So this Tn minus 1 is equal to what happens? Tn minus 1 plus 2n plus 2. All of you agree with me? That means Tn minus 1 plus, but we will write 2 into n, 2 plus 2, n plus 2, n plus 1. So if I think about that, 2n plus 2, so if I cancel all this value, suppose if I cancel this constant, because I have one n value, so I can convert this asymptotic notation, so I can only take n. So that what happens, when my n is greater than 0, this is n minus 1 plus n, and when my n is equal to 0, it produces only one time. When my n is equal to 0, it will just once check, so that it will be 1. So this is called total time. Everywhere we have to calculate this, then we can find out the time complexity. I can explain some different algorithm. Here I can take 2 for loop, here I can take n by 2, or here I can take half of that, or incremented by 2 or 3. Different approaches we can take, and according to that we can find out the total time. That's the beauty of this algorithm. So now our job is to find out the time complexity from the total time. How we calculate? There are 3 methods. One is called the decision tree, another is back substitution, and another is master's theorem. So today I will try my level best to explain these two. If time permits, then otherwise in the next class we will discuss, right? Now, so similarly, if I get the total time, now from total time we will try to find out the time complexity as well. This is a beautiful example and explanation by I will try my level best to explain you in detail, right? Now here, decision tree. What you have in the last slide, Tn minus 1 plus n. Now if I take it decision tree, that means we have like this plus this. So how, what value you have? T n minus 1, you can go to the previous slide, T n minus 1, T n minus 1, T n minus 1 plus n, am I right? Now if I do this one, T n minus 1, two part, I can put n, and here I can do T, here it is Tn. So Tn is equal to Tn minus 1 plus n. So similarly, if I again decision tree, I can put this one. So this will be n minus 1 and here it will be T n minus 2. N minus 2. Similarly, we can move on. We can move on. So we can calculate. I have give one example here and I have find out the time complexity. So here it is, what happens? Here it is n Tn minus 1. Now it is n minus 1, n minus 2, n minus 2, n minus 3. Similarly, if we move on at end, what we can get? T2, 2, Tn again minus 1, 1, T0, end. Now if we calculate the totality of this one, so what we will get? We will get 0, then 1, then 2, then 3, then 4, 5, 6, 7, 8, 9, 10 up to n minus 1 plus n. So this is a, I think you can guess, this is a completely a series. So what we have? 0, 1, 2, n minus 1, n. So this is actually a sum of the natural numbers, n into n plus 1 divided by 2. So here if we calculate n square, plus n divided by 2, we will take the maximum values what we have got, n square. So we call it as, in the worst case time complexity, this will produce order of big O of n square, big O of n square, or this is equivalent to the universal time complexity theta of n square. That means in a maximum case, this algorithm, in a worst case, this algorithm completes its job in a order of n square time complexity. So this is a complete mathematical derivation by the decision tree. So this is very simple example. We will try to evaluate. The next one I will show you, that is called back propagation algorithm. That is one of the beautiful algorithm. By that we calculate the time complexity, right? Now if we move on to the same time complexity we will take, and we will find out the back propagation. How we move on back propagation? Just a minute, we will explain in detail. We will try my level best to explain you in a very lucid manner. Now, back substitution or induction method, or back propagation or back substitution. I have taken the same example. This is Tn minus 1 when n is greater than 0 or is equal to 1. Now I have taken Tn minus 1 to start with, right? Now what I have in my hand? Tn minus 1 plus n, Tn. So in the right hand side, I have taken Tn is equal to Tn minus 1. Now from Tn, I have subtracted 1. So this Tn is equal to Tn minus 1. So that is called back substitution. That means I have each and every step I have substituted one step, right? Sorry. Now, so from here I have minus 1, so Tn minus 1 is equal to, here also I have minus 1, so this is Tn minus 2, and this is n, so that this will be also n minus 1, this is n minus 1. So I have got this one. So similarly, I have got Tn minus 1 is equal to Tn minus 2 plus n minus 2. In place of Tn minus 1, I have substituted this one, Tn minus 1. So what I have got? Tn minus 2 plus n minus 1 plus this n as usual. Again I have substituted Tn minus 1 minus 1. So Tn minus 2, Tn minus 3, n minus 1, n minus 1 minus 1, so that this will be n minus 2. So this Tn minus 2, in place of this Tn minus 2, I will substitute this Tn minus 2. So I will put Tn minus 3 plus n minus 2. So I have put this same Tn minus 3 minus n minus 1 plus 2. Tn minus 3. I have broken this step, right? So actually this from here directly, or you can say that Tn minus 3 plus n minus 2 plus n minus 1 plus 1 n. So similarly, if I moves on, similarly Tn minus 3 minus n minus 2, n plus 1 plus n. So if we go up to, in place of this is now it is 2, then it is 3, and move on up to kth term. So similarly, if we move on to the kth term, what we will get? Certainly Tn is equal to Tn minus k plus n minus, again k minus 1, opposite direction, right? N minus 1, k minus 1 plus n k minus 2 plus, similarly when k will be completely 0, we will get Tn minus 1 plus n. Now assume when it will be finished, when k closes to the n, or n is closest to n, that means we are incrementing the value of k, 1, 2, 3, 4, 5, 6, 7, 8. So at some times k will reach to the n. So we assume that n is equal to k, that means n minus k is equal to 0. So in that case, the algorithm will stop. Now if I put this value, so what we will get? In place of that, in place of k, we will put n. So here it is, in place of k, we will put, excuse me, in place of k, we put n. So similarly, I got 0. Here in place of k, I put n. So this is n plus 1. So this is 0. This n will be subtracted. This 2 will be deducted. This n plus up to n minus 1. That means here I got 0. If you notice, here I got 1. Here I got 2, and so on. N plus 1 plus n. So don't you think this is again what we have got? 1, 2, 3, 4, 5, 6, 7 up to n minus 1 plus n. So this is what? Sum of the n natural numbers. The sum of the n natural numbers, again I can say that this is big O of n square. The maximum time it will take, that is called the big O of n square. So this is the time complexity that we calculate using the two basic algorithm, like decision tree and the back propagation algorithm, and this is all about the time complexity, recursive in nature. Another method that is called Master's theorem, I will teach you in my next slide. Thank you all of you. Thank you my viewers. Thank you my students. I always appreciate your effort, and thank you all. Myself Dr. Subhankar Joardar. I am head of the department Computer Science and Engineering, Haldia Institute of Technology. Thank you.